Hey everyone, and welcome. Ever looked at a piece of complex machinery and wondered, how on earth do they know exactly how it's going to move? Well, the secret sauce is a really powerful mix of trigonometry and vector algebra. In this session, we're going to do a quick refresher on these essential math tools. The goal here is to get you fully prepped and confident for using the vector loop method in your linkage analysis.
So what's our main goal here? At the core of it all is something called the vector closure equation. Just think of it like this. If you walk around a closed loop and end up back where you started, your total displacement is zero, right? It's the same for these mechanisms. For a classic 4-bar linkage, this simple idea gives us one vector equation. We then break that down into two simpler scalar equations. From there, we use a bit of algebraic cleverness to boil it all down to a single trig equation with just one unknown angle. And here's the magic trick. We use what are called half-angle identities to morph that tricky equation into a basic quadratic polynomial that we can actually solve. Mastering this process is honestly the key to everything.
To really get a handle on the vector loop method, we're going to build our skills in two parts. First, we'll dive into our trigonometric toolkit. This is where we'll find the real power tools of math, some key identities for simplifying equations, the good old quadratic formula, and a secret weapon called the tan2 function for getting angles just right. Then, we'll get fluent in the language of vectors, which is how we'll describe and work with the physical parts of our mechanisms.
All right, let's get right to it. Time to open up that first toolkit and get our hands on the trig tools we need to solve these position equations. Now, two identities are the real stars of the show here. First up is the Pythagorean identity. This is our go-to for when we need to get rid of an unknown angle entirely. You just isolate the sine and cosine terms, square them, add them up, and poof, the angle's gone. It cleans things up nicely. Then we have the half-angle identities. These are like a magic wand. They take a really messy transcendental equation, one with sines and cosines all over the place, and they transform it into a friendly quadratic equation that we can easily knock out with the quadratic formula.
And of course, we've got the law of cosines. This one is a classic cornerstone of geometry, right? It gives us that direct link between the lengths of a triangle's sides and the cosine of its angles. Now, while the vector loop method is our main approach, the law of cosines is super valuable for a quick sanity check on our work and just for understanding the geometry of what's going on.
So, after all that work with the half-angle identities, we've got ourselves a nice quadratic equation. But here's where it gets really cool. That little part under the square root in the quadratic formula, the discriminant, it actually tells us a story about the real physical linkage. If it's negative, that means you have an impossible linkage. It just can't be built. If it's zero, that tells you you're at a critical point where two different ways of assembling the linkage merge into one. And if it's positive, boom, you've got two distinct, valid ways to assemble your mechanism. This is literally where the math meets the metal. It's so powerful.
Okay, so we've solved for our unknown, but now we need to find its actual angle. And this is a classic spot where people get tripped up. A simple arctangent function just won't cut it. It's like having a compass that can only tell you if you're going north or south. You're missing the whole east-west picture. That is exactly why we use the two-argument function tan2. It looks at the signs of both the x and y components, so it knows exactly which quadrant the vector is in. It gives you the full, unambiguous 360-degree picture every single time. It's a game changer. All right, our trigonometric toolkit is fully stocked. Now it's time for part 2, learning the language of vectors. This is how we're going to model the actual physical linkages that we're analyzing. Any 2D vector is really just defined by two things, its length and its direction. And we have two main ways to talk about them. There's the Cartesian system, which is like giving directions in a city. Go 3 blocks east, then 4 blocks north. Then you have the polar system, which is kind of more like a pirate's map. Go 5 paces in that direction. We need to be able to switch between these two languages fluently. And guess who shows up again to help? Our trusty tan2 function is absolutely essential for getting that direction right when going from Cartesian to polar.
When you boil it all down, the vector loop method is really just about adding a bunch of vectors together. A great way to visualize this is the head-to-tail rule. You just line up your vectors one after another like cars in a train. The final sum, the resultant vector, is just the vector that goes from the very beginning of the train to the very end. It's a really simple, powerful way to see what's happening. And the math behind it? It's just as easy. You just add up all the x components, and then you add up all the y components, separately. That's it.
Okay, just two last little vector tricks we need in our back pocket. First, finding the distance between any 2 points. It's as simple as finding the length or magnitude of the vector that connects them. Second, what if you want to completely reverse a vector's direction? You just multiply it by -1.
In Cartesian coordinates, that's as easy as just flipping the signs of both the x and y components. Simple as that.
All right, so we've reviewed the theory, right? We've got our trigonometric tools and our vector concepts down. Now let's talk about how we actually go from all this theory to practice.
And there you have it. Your toolkit is officially assembled. But you know, the best way to really let these concepts sink in is to play with them. There are some fantastic, interactive, open-source tools online that let you get your hands dirty. You can visualize coordinate conversions, you can see the atan2 function doing its thing in real time, you can even build a virtual 4-bar linkage and see how the equations we've been talking about actually make it move. I highly, highly recommend you go check them out. It's the best way to build that deep intuition that you just can't get from a textbook alone.
And that brings us to the end of our math review. Thanks so much for joining me on this journey. I hope you're feeling a lot more prepared to tackle kinematic analysis. And with that, I'd love to open it up for any questions you might have. Let's talk about it.